Alright, welcome to section 1.2, and here we're dealing with the ruler postulate. The ruler postulate is pretty straightforward. It basically says every segment has a length, and you might be thinking, duh. I'll write the word duh over here. Alright, duh, every segment has a length. Of course every segment has a length. There actually is quite a bit more to the ruler postulate than that, but this is really everything we need to know for now. And if you have more questions about it, or if it ever comes up and it's important, then I'll talk with you about it. But there is something that comes out of the ruler postulate that is kind of important, and that's a little bit of notation here. We've talked about segments, segment AB with that little line over the top. Now, this is the name of a segment, but since this segment now has a length, we need a way of talking about the length of segment AB, and so we write that simply as AB with no line over top. So here, name of the segment, over here, length of the segment. So when you see AB with no line over top, what you're talking about is a number. It is a number. It could be 5 or 10 or pi or anything, but it's a number. This is always a number. This over here, this is a name. AB, segment AB is the name of a segment. Over here, this is a number. So, a segment has a length. What does that mean? Well, depends. We've got a couple of different geometric worlds here. One of those worlds is I guess what we'll call the Euclidean world. That's where we don't have a grid. When we did those constructions in GeoGebra, that first construction anyway, unless of course you're in one of the classes that didn't do that. Anyways, that's just blank paper, just drawing pictures on blank paper. Circles, lines, segments, blank paper. In this world, segments have, I guess what I call a relative length. So one segment could be twice as long as another, or maybe 1/3 as long as another, but none of them actually has an exact measurement. In that case, you could sort of blow the diagram up, make it big, shrink it down and make it small. Either way, a segment that's twice as long as another will stay twice as long as another, but it doesn't matter how long they actually are. On the other hand, we have analytic geometry. And this is geometry in a grid where we've got coordinates. And in this case, we do have exact lengths. If we're measuring the length of a vertical segment, we'd say that the distance between A and B is the difference between, that's what subtraction is, the difference between the y coordinate of the A segment, the y coordinate of the point A and the y coordinate of point B. And then we take the absolute value of that. So we basically take the y coordinate of one point minus the y coordinate of other and take the absolute value. And actually it doesn't even really matter. You know how you can flip a segment name around? You can flip its length symbol around too. I call this BA, it'd be the same thing. And I could switch these around. It doesn't matter in the end. And we'll actually look at an example of that in a moment. Down here, if they're horizontal, well, then we take the x coordinates. So the distance between A and B is just the difference, that's subtraction, between the x coordinate of A and the x coordinate of B. And the same deal here. We could also just kind of flip them around. It wouldn't matter which comes first, which comes second. Now, we also have, just toss this in here, what if the segment's diagonal? Not everything is perfectly vertical or perfectly horizontal. In fact, most segments aren't. What do we do in that case? It's coming up in the next section. So let's take a look at examples of segment length. Here I've got AB, and here I've got DC or CD. AB is a vertical segment, so in order to find its length, I have to subtract one of the y coordinates from the other. You notice your y coordinate tells you how far above, or maybe in this case below, the x-axis you are. So the y coordinate tells you you're up, down. How far are you up and down? So obviously anything that's vertical, going straight up and down, its length is going to depend a lot on these y coordinates. So we take them, y sub a, y sub b. I've got 3 for our y coordinate here. I've got -3 for our y coordinate over here. And then 3 minus negative 3, subtracting a negative is pretty much the same as adding a positive, so 3 plus 3 is 6, and this is absolute value. Absolute value is just how far away is a number from 0? 6 is 6 units away from 0. Now over here, if I'm going to find the distance between D and C, now these are horizontal. The x-coordinate is what tells us how far left and right we are, so that's what's going to determine that horizontal distance. So over here, AB, we've got x sub d minus x sub c. X sub d is negative 4. Over here is negative 4. And x sub c is 2. And there's our 2. So we say x sub d minus x sub c, negative 4 minus negative 2. That turns out to be negative 6. And this is the absolute value of negative 6. An absolute value, again, is how far is a number from 0? Well, negative 6 is 6 spaces from 0, so its absolute value is 6. Well, if you'll notice here, these two segments that we just looked at are the same length. And we have a word for that. It's called congruent segments. Congruent segments, and we're going to see this word congruent come up a lot. Congruent always deals with things that are somehow the same, right? In some way they're the same. So congruent segments are segments that are somehow the same. Well, segments don't have a lot about them. They don't have a lot of properties. They really only have length. And so congruent segments are the same length. Here, we have a statement. Two segments are congruent. So we've got segment AB with a line over top. And this symbol here means is congruent to. Segment DC, again with a line over top. And that means that the distance between A and B, that's AB with no line over top, that's a segment length, it's a number, is equal to, and only numbers are equal, right? Segments, they're not equal. They might be congruent, but they're not equal. Equal means nothing with segments. Equal only applies to numbers. So the distance between A and B is equal to the distance between D and C. Now this funny symbol here, what this basically means is, this is, by the way, it means if and only if. It's a biconditional, but don't worry if that makes no sense to you and means nothing. We're not going to worry about it right now. What it means is that if I tell you that two segments are congruent, you can conclude that they're the same length, right? The arrow goes to the right. However, if I tell you that two segments have the same length, you can conclude that they're congruent, which means the arrow goes in the other direction. Now finally that we've talked about segments and their lengths and what it means for two segments to be congruent, that they have the same length, we can now talk about the segment addition postulate. By the way, we've seen this word postulate a couple of times. Basically, the word postulate, it refers to a claim or a statement that we're just not going to ask any questions about. We're just going to accept it. It's true. All right? Not going to worry about it. Don't ask any questions about whether the postulate is true or not. The segment addition postulate, now we could phrase this in a more complicated way like the book does, but basically it means the parts of a segment add up to the whole. Star, which basically means that there's all sorts of things mathematically wrong about what I just said, and I would love to clarify them, and we will. But for now, the parts of a segment add up to the whole is good enough. So look here. For example, I have AB, the distance from A to B. I've got this big segment here, A to C. The distance from A to B, just from A to B, that's 5 units. By the way, ignore this grid in the background. It's nothing to do with my units here. And BC is 7, so the distance from B to C is 7. So the distance from A to C, the whole distance, is equal to AB plus BC. So AB is this portion right here, and BC is this portion right over here. And so basically the complete distance all the way across the segment is equal to the two parts added together. Or in this case, AB is 5, BC is 7. And when I add them together, I find out that AC is 12. Or we could kind of use it the other way around. Where was it? Oh yeah. Over here we have MP, the distance from M all the way to P, is equal to 15, and NP, just from N to P, that's 10. So we have MP, that's the entire distance, is equal to MN, the length between m and n, plus np over here, then we fill in the blanks. Well, we know mp is 15, and we know that np over here is 10, so we fill those in. Then we'll subtract 10 from each side, and finally we have 5 equals mn. As a little bit of a side note, eventually when we start doing proofs about this kind of thing, you're going to do some sort of work like this. You're going to say, oh, okay, well, you know, MP is 15, NP is 10, and then you're going to write, without showing all this work, you don't have to show all this work, you're just going to say MN is 10. And someone's going to ask you, how do you know that? And you'll say, segment addition postulate. Right? That's your reason for knowing what that last segment length is. Right? How do I know that? I don't have to show all my work. I just knew I used segment addition postulate. Alright, then we have a last little smidge here, segment addition with algebra. So here, instead of having numbers, I've got expressions. So 3x minus 2 is AB. So the distance from A to B is equal to 3x minus 2. I don't know what that works out to, but if I knew what x was, I could do the work. So if, like, you know, x is 5, then 5 times 3 minus 2, the distance between A and B would be 13. Right? If x was 5. That's just an example. So without knowing what x is, we can't figure what the actual length is. But if we knew x, we could figure it out, and this would work out to an actual number. It would have some value. Over here we have BC, and BC is 2x plus 1. So if we knew what x was, we could figure out what that was. We could plug it in and evaluate it and figure out what that length was. And here you're asked to write an expression for AC. So I know the expression for AB, I know the expression for BC, and I'm supposed to write an expression for AC, the whole thing. I know the two parts, part 1, part 2. What's the whole thing? Well, AC is equal to AB plus BC, so the whole is equal to the two parts. I know that AB is 3x minus 2, and I know that BC is 2x plus 1. So I'm just going to add them together. I'm going to say 3x minus 2 plus 2x plus 1, and I got to figure out what that is. Well, I got some like terms to combine. I have 3x here, I have 2x here, and that combines to make 5x. Then I have negative 2 and positive 1. That's like going down 2 degrees and up 1 degree. That leaves me at negative 1. So all in all, the entire distance from A all the way to C is equal to 5x minus 1. Let's look at another one here, just a little bit more complicated, but not a big deal, it's doable. Here we have that MO, that's the distance from M all the way to O. That's 5x minus 2. Again, we could figure that out if we knew what x was, but we don't. But as soon as we do, we can plug it in and figure it out. How far is that actually? That's MO, the entire length of the segment. And here, NO, well, that's 3x plus 5. That's the distance just from N to O. And we're trying to write an expression for MN. MN. So down here we say, well, MN, that's a little bit here, that's equal to MO minus NO. Or the whole entire segment, take away this part. That'll leave us whatever's left over. That's another way of, using segment addition. So here MO is 5x minus 2, MO, 5x minus 2, MO. Over here I have NO is 3x plus 5. So 3x plus 5, that's NO, NO. So the entire distance, take away NO, will leave us with MN. And that makes MN 2x minus 7, because 5x take away 3x is 2x, and negative 2 take away 5 is negative 7. Now part of the reason why we're doing this is because later on in the future, you might be told, well, the length of this segment here is 2x minus 7. The length of this segment is 3x plus 5, and the entire segment is worth 22. Just making that number up. But I could set up an equation where this, some expression in x, 5x minus 2, or well, that's not what I used here for MO. I'd say where are we at? MN 2x minus 7. So the 2x minus 7 plus the 3x plus 5 equals, 25. And then I would have to solve that equation and figure out what exactly x was. Then I might be asked to go back, figure out what x was, plug it in here, and then figure out what the actual lengths were. So, just to recap, we've got segment addition postulate, which tells me I can add up the parts of a segment to make the whole. And how do I know that the segment parts have lengths? Well, that's all about the ruler postulate that we started out with. The ruler postulate tells us that these segments have lengths. And also, and this isn't on this page, but if we want to calculate those lengths, we have a method where we subtract the x coordinates or subtract the y coordinates if the segments are in the coordinate plane. If they're not in the coordinate plane, they have a whole different story, a whole different ballgame there. Also, if the segments happen to be diagonal in the coordinate plane, then the subtracting the x and y coordinates thing doesn't work. We have to come up with something else. And we'll talk about that later on. All right.